Welcome back to Professor Saad Explains. Today I want to talk about scalars, vectors, and tensors. For some reason, it's very easy for us to understand what a scalar is or even what a vector is, but comprehending what a tensor is always carries some risk. So today I will try to give you a framework on how to think about tensors and how to consider them as part of your arsenal in analyzing physical and mechanical systems. We are all familiar with scalars. These are just numbers. They describe things that don't necessarily have a direction. For example, you measure the temperature in your room. One point of your room, you say T is equal 28 Celsius. Doesn't make sense to say that the temperature is 28 Celsius due east and 25 Celsius due west. That just doesn't make sense. It doesn't matter where you're looking at, it's just the temperature at that point. However, it's so easy for us to understand that and to also understand that when things are moving, you also have a value associated with them, but also a direction. So take a basketball flying in that room, okay? So if it's going this way, you'd know that you'd say that the speed of the basketball is v, well, let's say 10 meters per second, and is going at a 45-degree angle, so gives you the direction of the coordinates. Or if it's going that way, that's a different direction, right? So it's very easy to comprehend what vectors and scalars are. Now, step back for a minute here. In fact, scalars and vectors and tensors there are all called tensors. Okay. With a scalar, we needed, beyond the value of the quantity we're measuring, we needed no additional information. No additional information was needed. For a vector, we needed a magnitude and a direction. Okay? So for the scalar, we only needed the magnitude, right? No additional information was needed. Now, both scalars and vectors are actually tensors. What differs between them is their rank. Okay? So the rank of a tensor is the amount of information needed to fully specify a quantity. That's really great because that tells us how to classify scalars and vectors. So for scalars, the rank by definition is 0. There's no additional information beyond magnitude. So we don't count the magnitude as a piece of information because any quantity is going to have some value associated with it. A magnitude or a component, some value associated with it. So we don't count that towards the rank. So scalar, given that it only has a magnitude, no direction, no other information, then it must be of rank 0. Vectors are of rank 1. Why? Because in addition to the magnitude, or the length or the size of the vector, we need directional information. So this one is given symbol, let's say alpha or u. This one would be ui. It needs one index to specify it. Okay. Now tensors have dimensions as well, and dimensions correspond to your space, for example, maybe time. Okay, depending on the physical field you're in. So vectors can be in 2D or 3D or more. They have components in them, and the number of components, the total number of components is equal to the dimensions, d to the power rank. Okay, so for a tensor of rank 1, such as a vector in 2D has 2 to the power 1 components. Vector in 3D has 3 to the power 1 components, so 3 components. Okay, so now we get to rank 2 tensors. To be very specific, we call those colloquially tensors because they're predominantly used. But really, what the heck are rank to tensors. To explain this with an example, I'm going to take this elastic band, just this piece of it. Okay. Now, this band is very thin, as you can see, so we can be in 2D. It's easier to explain this. And I want to look at the ways that I can stretch and deform this band. Okay, so I'm not thinking what you're thinking right now, the stress tensor, etc. Forget about all that. Just focus on the exercise of mental accounting for multiple things that can happen at once. Okay. So with this rubber band, I can stretch it this way, right? So I'm stretching on these sides laterally, okay, in this direction. I can also stretch it sideways like this, right, on these sides over here. But I can also grab it this way and stretch it this way or these two ways, okay? So if we were to draw this in a diagram, let's do this, draw this on a diagram, we would have this little rubber band, okay? You could push or pull in this direction, right? Or you could push and pull in this direction. And you could push or pull sideways in this direction. So on this face in this direction, on this face in these directions. So in total, we have 4 ways of stretching and deforming this rubber band. So if you were to give me some rubber band shape that looked like this somehow, to fully characterize this, I need at least to know what is happening on this face in this on this face in this direction, and on this face in this direction, and what's happening on this face in this direction and in the normal direction, because these sides are the same as the others. So I need at least 4 numbers to fully characterize the state of this deformable object. Okay? So now, if we wanted to describe that state with a single quantity, just for the sake of simplicity, just accounting for things, okay, what could we do? Well, it's rather simple. We could identify what we need to do that description. So we need to know on which side we are pushing or pulling, and in which direction we are pushing or pulling. So there are these faces over here that correspond to the lateral direction, and there are these faces over here that correspond to the transverse direction, right? And there's the x direction, right? The x direction and the y direction as well. So what we're going to do, I'm going to use a common convention and call these faces as x faces. Okay, this is an x face, x face. An x face is perpendicular to the x-axis. Okay, x, y. And we're going to call this one y face, y face. Okay. Now, because we said we have 4 ways we can stretch and deform this, so we can stretch and pull on the x face, or shear up and down on the x face, and we can stretch and pull on, push and pull on the y face, but we can also shear sideways on the y face. So there are really 2 indices to keep track of all of this. So if we were to call the x direction x and the y direction y, the x face x, the y face y, if we were to call the state of deformation in this body, give it the symbol tau fd, where f corresponds to the face that is being stretched or sheared or pushed, and d is the direction, then we can fully characterize with a single object that has 2 indices, we can fully characterize the state of forces in deformation on this rectangle. So here's how it goes. I'll draw this again. This one is going to be called tau xx. Remember, our nomenclature was tau face direction. The first index corresponds to the face on which is acting, and the second symbol, the second index, corresponds to the direction in which it's acting. Now, you might have asked, well, is there minus x? No, there's no minus x, because the value of tau xx will tell you if it's in the minus or the positive direction, okay? Now, this would be tau xx. This one over here would be tau yy, right? Tau yy. Tau xx. Okay, great. What about this guy over here? This is the force acting on an x face in the y direction. So this would be tau xy. Okay, could put here tau xy just to make them all symmetric. And we could put over here, this is the force, I want to say stress, acting on the y face in the x direction. So this would be tau yx, and this would be tau yx. Now, this is just accounting. This is just mental accounting of 4 quantities that are fully needed to describe the deformation state of this object. Turns out that this is actually a tensor of rank 2. Okay? In 2D, there are 2 dimensions, and we have rank 2. So in total, we have 2 to the power 2 components in 2D. And 3 to the power 2 equal 9 components in 3D. Not all quantities that can be combined into this kind of accounting are actually mathematical objects that are called tensors or even vectors, okay? There are quantities that are pseudotensors or pseudovectors. That's beyond what I want to talk about. But know that the state of stress in a fluid or in a continuum solid is actually a tensor. It obeys certain transformation rules, and it is an actual tensor.